Hello everyone, it's a great honor to share the research about secure learning adversarial autonomous driving environment here with you. My name is Bo Li and I'm an assistant professor from UIUC. As we all know that machine learning has been ubiquitous in the world, it has been applied to different domains to make our life better. For instance, autonomous driving, intelligent medical treatment, and smart city have been developed. And also the AI-induced control systems have seen a lot of great success recently. However, even such very powerful machine learning techniques can bring us a lot of security and privacy concerns. For instance, in 2016, the White House Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked, which triggered the automated trading bot to dump a large amount of stocks within seconds and swipe about $136 billion. And also, we have heard a lot of news about the accident caused by autonomous driving vehicles, which failed to detect objects such as trucks or some other possible scenarios, for example, pedestrians. So in this real-world examples, we can see that machine learning actually can also bring us a lot of security concerns. And in this talk, I will mainly focus on different components of the autonomous driving vehicle and mainly focus on the sensing and the control part and discuss what's the vulnerabilities of them by generating physical, possibly adversarial attacks, and then discuss the potential defenses against such attacks. In particular, in this talk, I will mainly focus on discussing the physical attacks against the camera-based sensing models, and then talk about whether the widely applied multi-sensor fusion systems are robust against such physical attacks or not. And then we'll discuss about the potential defenses against these attacks. So first, let's look at the threat model that will be discussed through this talk. Basically, either it's a single sensor or it's a fused sensor systems. As an attacker, the goal of them is trying to generate a so-called physical realistic adversarial object, and when giving such object to any sensors, and their output will be either the adversarial targeted labels or they will just ignore the object, such as cause the cars to crash into the object and cause severe consequences. So first, let's look at the vulnerability of the camera sensors. So here is an example of some stop signs taken from the real world. One is from Vancouver and one is from Berkeley. And we can see that usually in real world, there are a lot of, say, the graffitis and certain random patterns on the stop sign. So this makes us think, what if these random patterns are adversarial? And whether we can generate the robust physical attacks under different physical conditions that can consistently fool a machine learning model that could potentially be equipped in an autonomous driving vehicle. Based on this motivation, we will first look at what attack strategy will look like that will be able to satisfy this task. So first, let's look at a simple example first. So given the example of digital domain, for example, given say the target model f theta and the binary instance x, and our goal is to optimize the perturbation delta here such that the magnitude of the delta is minimized so that it will not cause humans notification, and then the adversarial instance, which is x plus delta here, will be given to the target model such that the model will make adversary run predictions to predict the label for the adversarial instance to be y star, which is the adversarial target. So you can see that by minimizing this simple objective function, we will be able to optimize the best delta here to fool this specific machine learning model. However, as we mentioned, there are a lot of physical conditions if we want to generate a physical adversarial example. For example, there are many different physical scenarios, for example, different distances and angles and lightning conditions we need to take account. And also, in realistic, we do not want the perturbation itself be of so low magnitude. We hope it's of some meaningful shape, such that the camera can capture the perturbation, but for human it will look like just the graffiti or random pattern, right? So based on this goal, we'll discuss this improved loss function. Basically, it is trying to use the expectation over transformation, meaning that instead of this single loss function, we will draw a distribution, draw several instances xi here instead of the original x from a set of distributions, including the physical conditions such as angles and distances and lightnings. And then we minimize this objective function over this expectation such that this perturbation is kind of like universal perturbation, which will be able to fool the machine learning model under different conditions. So this kind of solve our first constraint that try to make the generated adversarial perturbation as robust as possible under different physical conditions. And next, we want to make sure the shape of the adversarial perturbation is meaningful and large enough or obvious enough that can be captured by a camera. So here we introduce the spatial constraint adversarial perturbation. Basically, we want to constrain the perturbation itself into this mask region, such that this mask region is of meaningful shape, and it will be called hidden in the human psyche, that the meaningful shape will not cause human notification, but the perturbation inside will actually fool the cameras equipped in an autonomous driving vehicle, for example. And here there is some tricks to generate the position for this mask. For example, we can use the L1 loss, like the LP becomes L1 first, to generate the sparse perturbation, such that we can find the most vulnerable regions on the original physical, say the stop sign. And then we can generate a perturbation inside this mask with L2 or other TV loss to smooth out the perturbation so that it makes more natural. So here are some examples we generated, and we evaluate this physical adversarial examples statistically. So basically we can see each row shows different physical conditions and each column shows different types of perturbation. And all the signs here are misrecognized as speed limit sign 45. And we can see the first row shows a subtle perturbation, and it looks like just fading out for human. But actually this pattern is already enough to fool the machine learning models. And similar for this right turn sign and some letters of love and hate. And most surprisingly, even such just simple white and black rectangles are enough to fool the machine learning models to misrecognize this stop sign to be a certain speed limit sign. And of course, as we mentioned before, the positions of those stickers are very important. We optimize this position with L1 loss, and then we smooth out the perturbation inside so that it becomes even actually just a pure colors, which is effective enough to fool the machine learning models. So this is interesting in the static environment. And next, let's look at some examples in the dynamic environment. So this is a dynamic example. So on the left-hand side, it is adversarial generated stop sign, and on the right-hand side is a control experiment with a vanilla stop sign. And we can see when the car driving by, look at the caption here, you can see on the left-hand side, it is consistently recognized as a speed limit sign 45. And similarly for different types of generated adversarial stop sign, and we can observe similar phenomenon that the stop sign will be consistently misrecognized as speed limit sign, while the caption on the right-hand side, which is for the control experiment, are correctly recognized. And besides this classification models, we also show that this physical perturbation is actually powerful enough to fool not only this classification but also object detectors. So here is an example in a different environment that the physical adversarial stop sign is tested against the YOLO object detector, and we can see from different angles and distances this stop sign will not be detected, while other objects can be correctly detected. Unless you go to very, very close with this stop sign, and actually it captures the word here, and it may recognize the stop sign, but it will be too late for the car to stop at that time. And more interestingly, people ask whether it is possible to generate black box attack, meaning that we assume the attacker do not have any access to the model architectures and parameters. And here we show it is possible in terms of we can just use a similar adversarial stop sign and test against another model, which is called adversarial transferability here, meaning you can generate a perturbation against one model and transfer it to another model. Usually it shows that it is very effective in terms of attack different types of model. And we also have some theoretical analysis to bound what's the probability for such adversarial transferability. And here we can see test the same adversarial stop sign against the fast RCN, and we can see similarly we cannot detect this stop sign unless we go to very, very close with the sign, which is too late for a car to stop. So here we can see that, okay, the camera sensor itself is very vulnerable, and it is possible to generate all types of this physical adversarial stop sign, physical adversarial object to fool the camera sensors. And next, we want to look at what if it is a LiDAR sensor instead of a camera sensor here. Because, for example, the adversarial stop sign we discussed before, even though it's a real-world object, but it's still on a kind of a planar object, which is more like 2D instead of 3D. And here we want to understand better in terms of can we generate a 3D object, either a point cloud or 3D mesh, such that it can fool given LiDAR sensors. And then we will discuss the sensor fusion later. And first, let's look at the point clouds. So basically, we know that the input of a LiDAR system is point clouds, and it will give the prediction for different point clouds as different classes. And here, as an attacker, the goal is to generate adversarial point clouds given the benign point cloud X, such that the adversarial point clouds X prime will be misrecognized as different classes by the sensor models, such that the distance between these two point clouds are minimized. For example, the distance here we can use either chamfer or Hausdorff distance. And by optimizing this objective function, it is possible to generate such X prime. However, when we can see that there are different strategies to solve this optimization problem. For example, we can shift the points near the surface of the point cloud, or generate some independent points adding, or we can generate adversarial small point cloud clusters or adversarial objects near the original objects. And what does that mean? Let's look at some examples. Here you can see, to human, these objects are all look like bottle, right? But here shows different adversarial strategies. For example, you can shift some points near here and also add some independent points, or you can just add some adversarial clusters or add some small adversarial objects around the original object here. And all of them can be misrecognized by PointNet as either chair, sofa, or toilet as a targeted attack. And more generally, we can see we can shift some points for the bottles, although all of them look like bottle to human, but the PointNet will misrecognize them as different targets, which is shown on the top. Basically, it shows that you can misrecognize these point clouds as arbitrary target as you want. And this is a more interesting example that we can potentially add some adversarial object clusters like the drone here near the original object, and the whole point cloud will be misrecognized as the labels on the top. So you can see this is showing that it is possible that you can fly some drones around the car in front of you, and the LiDAR equipped on your car may recognize the whole thing in front of you as other objects instead of a car, which is very dangerous. And based on the point clouds, we also look at whether we can add the rendering component to not only generate adversarial 3D point cloud, but also the 3D meshes. So here we can see similarly, we can generate this S means the 3D meshes given certain conditions to run this rendering system. So here we still use similar principle of the expectation over transformation, meaning that the condition here that's the illumination and the parameters inside the renders, we sample from a distribution such that we can fool this render system in a large distribution with the representative subspaces, so that the generated adversarial 3D mesh will be robust against the different render systems. And the goal is that after rendering, this adversarial 3D object will be misrecognized as the adversarial target. And just briefly, quantitatively, we can see that these types of adversarial 3D meshes will achieve very high attack success rate against the different models. And this is a simple example that as a adversarial 3D mesh, which looks like a car to human, but it will be consistently misrecognized as a hot dog with high confidence. And let's look at some real-world examples. Here is the goal, as we said, is to test the vulnerability of the single LiDAR sensor systems. And we can see here, this is a real-world example that we 3D printed out the generated 3D object here and put in front of the car on the highway. And we put a box with similar size at the same position here. And we will drive the car towards this object, and on the top it's about a benign object, and on the second row is adversary, and we give the input to the LiDAR systems equipped on the car, and we will observe that the car will always recognize this benign object, which is a box, but not the adversarial object here, as we can see. Like, you can see with the car driving by, this consistently shows the green box here, but on this row, the adversarial object can never be recognized by the LiDAR systems in real world. So it shows that it is possible the car will run into this object if the LiDAR cannot detect this object. And similarly, we put the car, put the object on the right side instead of in front of the car, and then we drive the car again. And we can see similar phenomena that the box can be detected by the LiDAR in the benign environment, but not the adversarial objects. So here we can see the single sensors, either its camera or LiDAR system, are actually very vulnerable. And people may ask that actually in practice, we always use multi-sensor fusion systems, and it's very hard to generate the adversarial objects which can fool multi-sensors at the same time, right? So, okay, to answer that question, we want to look into the vulnerability of the MSF systems and see whether we can generate a single object such that it can fool the multi-sensor fusion systems. So first of all, there are a lot of additional challenge to do so, because we can see there are several non-differentiable pre-processing or post-processing for the whole multi-sensor fusion pipeline, and also there are a lot of different non-differentiable cell-level aggregated features for different sensors. And here is an example of real-world Apollo autonomous driving platform with different pre-processing and post-processing for the whole entire pipeline. And the goal here is to generate a realistic 3D object, and we can print it out and put on the road. So it will be stealthy to human perception system, but physically realizable and also fool the multi-sensor fusion systems. So here we choose this cone here because in the original LiDAR systems, the cone is a very important class to be detected. And here you can see this is adversarial cone that is optimized and with 3D printed out. And similar to human, these two look quite similar in terms of the shape and appearance, but surprisingly, this is enough to fool the multi-sensor fusion systems. So let's look at briefly the whole pipeline. So basically, given the benign 3D objects like the cone here, we sample a set of distributions, for example, with different rotations and distances and angles, and along with the original benign instance, sent to the different sensors here. And here we take the example of LiDAR and the camera at the same time, and they will do some pre-processing in the whole pipeline and generate some adversarial object based on the adversarial objective function. And this object will be sent back to the original class and do the projections process, such that after this process, the generated adversarial object will be stealthy enough, and then we get a loop to go through it until the generated instance satisfies certain stop criteria. For example, the between the adversal object and the benign is minimized, and also the adversal object will have high attack success rate against the multi-sensor fusion systems. And next, let's look at some examples running in the Apollo simulation platform. And in the first row, it shows the benign object in front of the car, and second row shows the adversal object. And you can see for the benign object, after the car getting close to the object, it will detect it and stop for the multi-sensor fusion system. But for the adversal one, it cannot detect the object and just pass through it, which in reality will cause the car to crash into this object. And we have tested the object on different positions and observe the similar phenomenon. And if you are interested, I can post the website link there, and you can look at more examples from the website. And next, we want to discuss against all these potential physical attacks. We can see they are very powerful, and they can fool not only the single sensors but also the sensor fusion systems. We want to discuss what's the potential defense mechanisms against such realistic attacks. So here I want to promote this sensing reasoning pipeline. So as we remember, we have these sensor perception systems in autonomous driving vehicle, and the sensor detected result will be sent to the control component to help make further inference and predictions. So here is pipeline that in our research group, we propose that in the future or in industry machine learning at least, we should not use a single machine learning model to make predictions, because they are not reliable. We should use this pipeline, which is called sensing and reasoning. One potential way is that we can leverage the sensing reasoning pipeline to improve the robustness of traditional machine learning pipelines. So basically here we can see we have different sensing models. They can be either, say, cameras and lidars and radars, or they can also be different cameras equipped on different positions. So basically they observe the similar input and give the output and send to the reasoning component. And this reasoning component can encrypt such knowledge into the structures. For example, this can be Markov logic networks or Bayesian networks, and they incorporate the knowledge structures inside. For example, one potential input is this is a cat and this is water, and the inference here tells you a cat is swimming in the water, and then we will realize there must be some sensors has been attacked, because from the knowledge we know a cat may not be able to swim, right? So this way the reasoning component will be able to come back and correct some sensors based on the knowledge they have. So this is a basic idea on it. And one very nice property of this pipeline is that not only we can just improve the robustness of the machine learning pipeline empirically, here we can also improve and certify the robustness of this pipeline theoretically, meaning that given the perturbation magnitude of the input here, we will be able to give the bounded output of the neural networks here as a sensing robustness, and then based on this range of the output of the neural networks, we will still be able to certify the robustness of this reasoning pipeline, and therefore we will certify the end-to-end robustness given the input perturbation and obtain the output range of the final output. So this gives us some confidence to improve or certify the robustness of real-world machine learning pipelines. So this is very generic, and the knowledge here could be anything. For example, we can give the knowledge saying stop sign is always with a certain shape, and if other cars stop, you should also stop, kind of the knowledge like that. And next, I will give a very simple example of a kind of statistical knowledge in terms of the temporal consistency to improve the robustness of the object detectors against the video data. So for example, here we can see if we have some videos and if some frames are attacked, for example, some frames are adversarial examples, how we can detect the adversarial frames from these videos. So what we can do is that given the knowledge, as we know, the video data should be temporal consistent if it is taken under the same environment. So based on this, we generate this pipeline meaning that given different frames, for any two frame, we can analyze or predict the optical flow between them, and use this optic flow to generate a new frame, which we call the pseudo frame, based on the previous frame. And then now we have two frames. One is the true frame, and one is the pseudo frame, right? And then we can compare the, say, either it's a segmentation or object detector behaviors of the two frame and compare their consistency. So the hypothesis is that if the consistency of the two frame are very high, it means that this frame is not attacked. Otherwise, it is attacked. And statistically, we can see actually the benign and the adversarial frames can be very separable in terms of this consistency. And quantitatively, we can see if we leverage this pipeline to detect the adversarial frames, it almost detected with almost 100% AUC score, and even against the very powerful adaptive attackers who has known the whole defense pipeline. So let's look at some examples quickly. So there are different tasks like doing the segmentation, object detection, human pose estimation on the video dataset. And here we show different colors as benign and adversary and after detection, meaning that we detect and remove certain adversarial frames. And by looking different videos, you can see in the middle there are some adversary frames, but after detecting it and remove them, on the right hand side it behaves similar with the benign input. And similarly for the human pose estimation, you can see in the middle there are some frames adversary, but on the right hand side it looks totally benign, and similarly for the object detectors. So this shows that it is possible to improve the robustness of the machine learning pipeline effectively by incorporating some common sense or human inference knowledge. And these works have been discussed in different multimedias. And if you have any questions, you are welcome to discuss with me. Thank you.